We have all heard about evaporation at some point. What exactly is it? Evaporation is the process of a liquid substance transforming to its gaseous state when it receives external stimulation, generally in the form of heat. Heat energy is absorbed by liquid molecules, some of which break away from the linkages binding them to one another and are released in the form of vapor, or in other words, the liquid evaporates. A common example is the drying of damp clothes hung out in the sun. Damp clothes consist of water molecules bonded loosely with the cloth fibers. Energy from the sun and the wind flow through these clothes, carrying with them some of the water molecules, eventually drying the clothes. Simply put, clothes in the open dry due to evaporation. That was evaporation. What about evaporative cooling? When air passes over a stream of water, water vapor is added into air, lowering the air temperature. The energy needed for evaporation is taken from air, and the loss of energy is reflected as a reduction in the air temperature. This phenomenon is called evaporative cooling. A very common example is one we all experience on a daily basis: perspiration. As air passes over the skin, evaporation takes place and a cooling effect is felt. This is because the sweat takes away some of the body heat during evaporation. Now that we know what evaporative cooling is, let's look at the two types: direct evaporative cooling and indirect evaporative cooling. In direct evaporative cooling, warm air from outside is pulled through moist pads where it is cooled due to evaporation. The cool air with added moisture is then drawn to the space requiring cooling using a blower. The second type is indirect evaporative cooling. Here, we use a sensible heat exchanger as the medium. It consists of alternate panels allowing wet air streams and dry air streams. Water is allowed to drip on the heat exchanger into the panels allocated for wet air streams. The fans are switched on, and as warm air passes over the wet surface of the heat exchanger, water on it evaporates and the material of the heat exchanger is cooled. Air is then passed through the dry panels of the heat exchanger, where it is cooled by virtue of its interaction with the cool surface. This cooled air, without any added moisture, is let out at the other end. In indirect direct evaporative cooling, air is cooled first with indirect evaporative cooling and then cooled further with direct evaporative cooling. Psychrometry is the study of moist air, and psychrometric charts are the tools used to study them. Let's have a look at the elements of this chart and use them as a reference to understand evaporative cooling. Dry bulb temperature is represented on the x-axis and increases as we move from left to right. Wet bulb temperature lines are inclined and straight. They increase from left to right along the highlighted curve. Enthalpy lines are also inclined and straight and increase in the direction of the highlighted curve. Specific humidity is represented on the y-axis, increasing as we go upwards on the chart. Constant relative humidity lines are curved and increase from right to left. So moving towards the right or left on the chart parallel to the x-axis would be sensible heating or sensible cooling, where the dry bulb temperature changes without a change in the moisture content of air. Moving parallel to the y-axis would cause humidification or dehumidification, that is, changes in humidity levels of air without changing the dry bulb temperature of air. Moving perpendicular to the wet bulb temperature lines would cause a combination of cooling and dehumidification or heating and humidification. Moving along the wet bulb temperature line downwards would be heating and dehumidification, whereas upwards would be cooling and humidification, which is what happens during evaporative cooling. The basic principle of indirect direct evaporative cooling can be understood using a psychrometric chart. Indirect direct evaporative cooling involves treating warm air first with a sensible heat exchanger. This is the first stage, or the indirect stage, where sensible cooling takes place and we see a reduction in the dry bulb temperature without any change in humidity. In the second stage, or the direct stage, the air is cooled and humidified, as can be seen in the psychrometric chart. The dry bulb temperature is reduced further and humidity sees a slight increase here. Let's now have a look at the components involved. Louvers allow air to pass through it, keeping away unwanted elements like water, dirt, etc. Filters are used to filter out foreign particulate matter in air to ensure acceptable air quality. Water tank is used to store the water needed to fulfill process requirements. A float valve keeps the water level in check and prevents tank overflow. An air blower is used to blow cooled air into the occupied spaces. Heat exchangers facilitate heat transfer between air and water. We are now in a good position to learn how this system works. The water tank is filled and water is pumped up to the outlets above the heat exchangers. The fan turns on and draws in air from the secondary air inlet through the sensible heat exchanger. Outside air is allowed to pass through the primary and secondary air inlets. The primary air inlet has louvers and filters since air passing through this is going to be treated and delivered to the occupied spaces. Air from the two inlets never interact directly with each other. Warm air entering the wet airstream panel of the heat exchanger from the secondary air inlet becomes warmer as it gains some heat while vaporizing water off the wet surface of the panel. Air coming from the primary air inlet is cooled while passing through the cool heat exchanger panels. This completes the first stage or the indirect stage. Air coming out from the first stage then passes through the direct stage heat exchanger, the cellulose pad, where it comes in contact with a stream of water to further lose heat while gaining some humidity. The air at the outlet of this heat exchanger is drawn in by the blower and delivered via ducts to the spaces requiring cooling. Here we consider a room cooled by direct evaporative cooling on one side and a room cooled by indirect evaporative cooling on the other. Compared to direct evaporative coolers, for the same ambient conditions, indirect evaporative coolers can achieve lower temperatures with lower humidity while requiring lesser amount of water and energy, thereby proving to be both energy and cost efficient.